So ionic compounds. Ionic compounds occur in the Earth's crust as minerals, and they're also present in the foods that we eat. There are a lot of different ionic compounds. One thing I'd like you to take away from studying chemistry is the idea that anything can be toxic if you get too much of it, right? And we tend to have this negative connotation when we say, oh, well, that's a chemical. Everything's a chemical. Anything that is matter is a chemical. Water's a chemical. Is water bad for you? No. Unless you've got way too much of it, then it's bad for you. So are all chemicals bad? No. But you get too much, they're bad. So we shouldn't be afraid of chemicals, right? So here we've got ionic compounds. Morton's light salt, okay? Sodium chloride is table salt, but some people have high blood pressure and they're very sensitive to sodium. And so if they eat too much salt, they get too much sodium, their blood pressure goes real high. So light salt is a mixture of sodium chloride and potassium chloride, so that you can get the salty flavor without getting as much sodium. Tums, used for treating heartburn and having too much acid in your stomach. Calcium carbonate, that's a chemical. It's an ionic chemical. All three of these are ionic compounds. Here's some examples of what you might think of as rocks, right, from the Earth's crust. This is calcite. This is a different form of calcium carbonate. If you chew and swallow some of this, it's not really going to help your heartburn. This is in us, with other stuff, and so this is appropriate for treating heartburn. That isn't. You'll break your teeth on that one. This guy over here is called trona. It's a crystalline form of this compound. Here we've got sodium and some nonmetals. This is an ionic compound. So we're going to learn how to write formulas for ionic compounds. We'll go through the rules, if you will, and then we'll do examples. Learning this stuff is a bit like learning to play a new game, a card game or a board game. You read through the rules. We got some new games for Christmas, and you read through the rules, and you're like, I have no idea what they're talking about. It's not until you start to play the game and you make a mistake and get corrected by other people, and then it starts to make sense. You're not going to really know the rules until you've played the game for a while. So at first, writing these formulas and naming these compounds is going to just be like, wow, I'm lost. You just have to keep trying, keep practicing, and then it will become much, much easier. Okay? So reading the instructions for the game. For ionic compounds, we write the symbol for the metal ion with its charge, followed by the symbol for the nonmetal ion with its charge. This is the first step to knowing how many of each atom we have to put together. So we're going to put subscripts on each of the ions so that we get the overall charge to add up to 0. All compounds are neutral, which means you have to have an equal amount of positive and negative charge. So after we figure out what the subscripts are for each cation, then we're going to double check that the sum of the charges equals the sum. The charges of the cations equals the sum of the charges of the anions. That was awful. So ionic compounds always contain positive and negative ions. The first element is usually a metal. So this is the only exception that you need to know. Some ionic compounds contain the cation ammonium. So NH4 plus is a cation, but it's composed of nonmetals. It's a very common polyatomic cation, and that's why we're going to learn that one. There are others, but we're going to ignore them. So if the first element is a metal, it's an ionic compound. If you see NH4 at the beginning, it's also an ionic compound. In the chemical formula, the charges of the positive have to equal the charges of the negative. And the formula for ionic compounds reflect the smallest whole number ratio. essentially the empirical formula. Okay, so let's do a couple of examples. So potassium is a metal, sulfur is a nonmetal. We're going to write the formula for the ionic compound that forms between potassium and sulfur. So the first thing we need to do is write the symbol for potassium. So potassium is capital K. That's going to form a cation because that's what metals do. And then we need to write the charge. What's the charge on a potassium ion? +1. Because it's in group 1 of the periodic table. Sulfur has the element symbol S. It's a nonmetal, it's a negative ion. What's the charge on that one? -2. So this is S, 2-. Because if you look at the periodic table and start with the noble gases, you have to count backwards 2 squares to get to sulfur. So it's a -2. Then we have to figure out, well, how many of these and how many of these do I need so that when I put them together, their charges add up to 0? Some of you can look at that and immediately see, oh, I need 2 potassiums and 1 sulfur. That's great. Some of you can't. That's fine too. Brains work in different ways. So one method that students tend to like a lot because it involves less thinking, I think, is the crisscross method. So in the crisscross method, look at these charges. This is +1 and -2. It's not the same number. If it was +2, -2, we're not going to do crisscross. But it's different, +1 and -2. So what we're going to do is we're going to take, let me do a different color here. We're going to take the charge of this one and make it the subscript for the other one. This is an unwritten 1. It's going to become an unwritten 1 over there. And then we're going to take, we're going to take this charge, and that's going to become the subscript for the potassium. So we're going to end up with K2S. That works most of the time. Every once in a while it'll get you in trouble, but it works most of the time. You should always double check that you have the lowest ratio here. You can sometimes mess up and end up with, PB204. And 2 to 4 could be reduced, and so you need to do that. But that'll work most of the time. I'd also like to show you why the formula is what it is. So we've got a potassium with a +1 charge. We've got a sulfur with a 2- charge. So I'm just going to keep track of the charges I have down here. So currently, if I have one of each, I've got a +1 charge, and I've got -2. These numbers do not add up to 0. So there's more negative charges. That means I need more of these positive ions. I can't change the charge on the ion, but I can say, well, what if we had a second potassium ion? So if I put a second one in there, now the overall charge is +2. If I add +2 and -2, they add up to 0. So 2 potassium ions with 1 sulfur ion will give us a neutral compound. And so I look at how many of these I've drawn. I've got 2 potassium, so it's K2. I've got 1 sulfur, so I just write S. Any questions? Let's look at aluminum and nitrogen. What's the symbol for aluminum? Al. And what charge does an aluminum ion have? 3+. Because it's a main group metal and it's in group 3A, it's got a 3+ charge. Now, this L needs to be a lowercase l. So I'll accept this, that's fine. But sometimes students want to do this. They want to write their lowercase letters as small caps. Not okay. This also is not like this. Those are not acceptable. This one's fine. So we've got aluminum, and then we've got nitrogen. Nitrogen is N. What's the charge on a nitrogen ion? 3-. So here I'm going to look at the charges. I've got +3 and -3. I don't need to do anything fancy. The numbers are the same, the signs are opposite, I just need one of each. So I think of it as just pushing them together. So I've got AL and I've got N. There's no subscripts because I just have one of each. Any questions? Now what about naming these compounds? A lot of compounds have common names. Like we saw that crystalline substance, it was called trona, and then it has this big long formula. So trona is a common name. Some compounds have common names, but chemists have developed systematic names for everything. So every compound has one best name, and then it may have some other names. It's just like each person has a given name. You have the name that is on your birth certificate, right? It might not be the name you actually use, but that is your one true name, right? So the systematic name is like your birth name, the one on the birth certificate. There are different systems of naming compounds for different types of compounds. Just like people in different countries use different systems for naming their children. Some countries, it's very common for people to have a single name. They don't have a first name and a last name. They have one name. In some countries, your family name is first and your individual name is second. That's the reverse of what happens in the United States. So there are different systems. To understand the names, you have to understand what country this name is coming from. So ionic compounds have their own system for naming. We have to identify this is an ionic compound before we can apply that system of naming. So again, ionic compounds, usually metals and nonmetals. The one exception is ammonium, NH4. So examples of ionic compounds here. All of these are starting with a metal. They are all ionic compounds. Ionic compounds, we can say there's two types depending on the metal. I think this distinction is a little bit silly, but I'll try to go along with it because it is in the book. Some metals have an ion name that is the same as their element name, and some metals need to have like a Roman numeral on them because they can form more than one charge. So some elements, some metals, can form more than one charge on their ions. So I think of this a little, yeah, question?
Like copper?
Like copper. Copper can be +1 or +2. And so we can't just call it copper ion because then we don't know which one we're talking about. But potassium ion is always +1. So when I say potassium ion, everybody's going to know that's +1. So I don't need to specify which kind it is. I think of this naming of these metal cations is a little bit like naming guys, right? So maybe there's Henry Smith, and there's Henry Smith Jr., and then there's Henry Smith III, and Henry Smith IV, right? You need the Roman numeral or the junior senior to tell which Henry Smith are we referring to in this same family. There's 4 of them, right? So some metals like copper, iron, cobalt, a lot of them actually, can form more than one charge. And so we use a Roman numeral, just like, the kings of England, Henry IV, use a Roman numeral to indicate which Henry are we talking about. So these are the metals that always form a single charge, that they only have one kind. And so we don't need a Roman numeral. We could, sometimes students are like, well, why can't we just write Roman numerals on everything? Well, I know what you mean, but, my son, Thomas Calagoa, he is the only Thomas Calagoa in the whole world. So why would I call him Thomas Calagoa the first? He is the first, but why, right? We don't just go adding suffixes like that unless they're needed. We don't want to complicate things. So it's like the number 1. If we don't need it, we're not going to write it. If you don't need a Roman numeral, we're not going to write it. These highlighted here are the ones that don't need Roman numerals. And I'm going to repeat this over and over and over. Groups 1A, 2A, 3A, zinc and silver. Groups 1A, 2A, 3A, zinc and silver. Those do not need a Roman numeral. All the other metals you should put a Roman numeral on. Now there's scandium sitting right here. I'm going to ignore him. Technically, he doesn't need a Roman numeral, but that will not come up on an exam. You won't lose any points. We're just going to ignore him. He's a very unusual element anyway, so we're just not going to see him. Groups 1A, 2A, 3A, zinc and silver. So metals in group 1A have a +1 charge. Metals in group 2A have a +2 charge. Metals in group 3A have a +3 charge. We're not going to run into these guys either. So here's aluminum in group 3A. It's a +3 charge. And then there's these two guys tagging on at the end, zinc and silver. How do we remember those? I think of these as being like going down the stairs. Right? Here you're on the top step, and then you go down a step, and you go down another step. This one's +3 because it's in group 3. I go down a step. What's down 1 from +3? +2. And I go down another step, and that's +1. So aluminum, zinc, silver, 3, 2, 1. Those are their charges. So groups 1A, 2A, 3A, zinc and silver, we know from their position on the periodic table what their charge is. No Roman numeral for their name. Okay? All the other ones are going to need a Roman numeral because they can form more than one ion. So there are two systems of naming. We can use the Roman numerals, or this is an older system. I'm showing you this because I want you to know that it exists, but I am not going to expect you to use it or to know, remember it. If one of these should come up in a homework problem, you should go, oh, that's that other thing. I'm going to go look up what the charge is. Okay. So chromium is not in groups 1A, 2A, 3A, zinc or silver. It needs a Roman numeral. Chromium can form two different ions. You are not expected to know which different ions chromium can form, just that it can form different ones. So I'm telling you it forms 2 and 3. You don't have to remember that. But Cr2+ is called chromium 2, and Cr3+ is called chromium 3. So we indicate the charge with a Roman numeral in parentheses right after the element name. So quick review of Roman numerals. For a 1, it's just a capital I. So that's 1. For a 2, it's 2 capital I's. For a 3, it's 3 capital I's. Of course, if you kept on going like this, how is that really different than just tally marks? And what do you do with 527? Well, let's skip 4 for a minute and go to 5. So 5 is a capital V. I don't know why. Ask the ancient Romans. They made this up. 4 is 1 less than 5, right? So it's an I, a 1, before a 5. 6 is 1 more than 5. So that we've got the symbol for 5 and a 1 after it. So it's 1 after 5. 7 is 2 after 5. And it kind of keeps going like that. That's enough. If you're okay up to 7, you'll be okay. So here's lead 4. So lead 4, it's got a 4+ charge. The Roman numeral is the charge on the ion. It's not how many of those ions we have in the formula. It's the charge. Okay? Any questions? Oh, I kind of already told you this, but here it is in a summary. So metals in group 1A and 2A form charges equal to the group number. This triangle is also predictable. So aluminum, if you should run into gallium or indium, those are in group 3A. They have a 3+ charge. Aluminum, zinc, silver. So this is +2, this is +1. Cadmium also falls in that triangle. It's +2. So if you see cadmium, it may not have a Roman numeral, and you may wonder about that. That's one of those kind of odd ones we're not going to run into. Yeah.
And boron will be plus,
Boron is a semi-metal, and so we're not going to see it forming ions. But that's a good question. So we're talking about the main group metals as having predictable charges. Hydrogen often has a +1 charge, but it's not actually a metal, and it can also form a -1 charged ion. So it's the metals we're talking about here. So metals in the triangle are predictable, but this is what it comes down to. Groups 1A, 2A, 3A, zinc and silver do not use a Roman numeral. Any other metal, put a Roman numeral on it. Okay? So those are the cations. Then there's the anions. So monoatomic means one atom. So there are anions that are just a single atom, and they've gained one or more electrons. These are named by taking the element name and changing the ending of it to IDE. So the element fluorine, we can find from its position on the periodic table, it makes a -1 ion. And so to give the name of the ion, we change the ending of its name. So this is how I think of it. I think of the nonmetals, I think of the metals as being masculine. They both start with M. There's a lot of other ways it works out. Metals are masculine. Nonmetals are non-masculine, so they're feminine, right? And this is being very, very traditional. Do not be offended. It just works with the pattern. So traditionally, the female, when two people get married, the woman traditionally changes her last name, right? Changes the ending of her name. So here, fluorine, I call it Mrs. K's chemistry land. In Mrs. K's chemistry land, fluorine is female, and so when she becomes part of a compound, she changes the ending of her name. She's fluoride now. The metals do not change the endings of their names. Traditionally, men don't change their names when they get married, right? So we take the ending and we change it to ide. So chlorine becomes chloride, oxygen becomes oxide, etc. And there's a little review of the predictable charges. Group number -1 or count backward from the noble gas column. Any questions? So we are going to learn how to name binary ionic compounds. These contain 2 elements. Binary means 2. So you put the name of the cation first, and then there's a space, and then the name of the anion, which is the nonmetal's name with the ending changed to ide. And it's always the metal first and then the nonmetal, the positive ion and then the negative ion. Just like when you address a formal invitation, it's Mr. and Mrs. John Smith. Why isn't it Mrs. and Mr.? It's convention. It's just how everybody's decided to do it, so it's easier when we all do it the same. It has no bearing on who's more important or anything like that. But there's this pattern. The metal first and then the nonmetal. Always. So, KCl. If we want to name this has a potassium ion and a chlorine ion. So potassium is in group 1A, doesn't need a Roman numeral. So the name for that ion is just potassium ion. And then we name the chlorine ion. So chlorine is a nonmetal, and it changes the ending of its name to ide. So potassium chloride. Most ionic compounds just have 2 names, just like most people have 2 names, a first name and a last name. So CaO, 2 ions, a calcium and an oxygen. So the name of the calcium ion is just calcium because it's in group 2A, it doesn't need a Roman numeral. Oxygen changes the ending of its name to oxide. Oxygen, while in chlorine too, those are diatomic elements, but here they don't need to be diatomic elements because here, instead of hanging out with their girlfriend, they're with the guy, right? Maybe they've grown up and gotten married, and so I'm with calcium now, and I'm okay. I'm not alone. I don't want to be alone. So I'm either going to be with a girlfriend, or another oxygen as a molecule, but when I hook up with a guy, I don't need the girlfriend. She's going to go off and find something else to do. Okay? So we don't put twos in here. The diatomic element business is just when it's the element, not when it's part of a compound. Any questions? So let's practice a little bit here. So name this compound. We've got 2 ions. We'll see that sometimes we have more than 2 elements. Here, we only have the 2 elements, and so it's not so bad. The first element, what's the name of that ion? Silver. Does it need a Roman numeral? No. Groups 1A, 2A, 3A, zinc, and silver. No Roman numeral. So there's the name of the first one. The nitrogen. How do we change its name when it becomes an ion? Nitride. If you wrote nitrogide, I'd know what you mean. I wouldn't mark it wrong. I might snicker a little bit, but I wouldn't laugh in your face. Nitride. So that's silver nitride. Questions? Yeah.
Why didn't it try silver nitride?
Excellent question. Why not try silver nitride? Because there's 3 silvers, right? We don't need to say try silver nitride because we know it's Ag3N due to the charges. So if we were given the name, we would write the formulas. So the silver ion, groups 1A, 2A, 3A, zinc and silver. Zinc is, aluminum's +3, zinc is +2, silver's +1. We know it's +1 from its position. And then we have nitride. We know from its position its charge is -3. So to put these 2 together, I need 3 silver ions to balance the charge on the nitrogen ion. And so the try is not necessary. We want these names to be as efficient, as succinct as possible. We don't want to put extra stuff in them. Okay?
So when is that prefix necessary for like dihydrogen sulfide or something?
Excellent question. So those numerical prefixes, tri, di, tetra, etc., come into play when we have nonmetals. When we have molecular compounds, because there are no charges to tell us how they get together, we need the prefixes to indicate how many there are. Excellent question. Any other questions about silver nitride? So here's going the opposite. We've got a name. Let's write the formula. Well, what's the symbol for rubidium? Rb. So what's the charge on Rb? +1 because it's in group 1. Sulfide, that's S, and what's the charge? 2-. So then we have to figure out, based on the charges, how to put these 2 together. You can do the crisscross thing, or you can say, well, I would need 2 of these, so I'd have a total of +2 charge to balance one of the -2 charges. So rubidium sulfide is RbS2. We don't need to call it rubidium disulfide because it's the charges that tell us what the ratio is. Any questions?
Isn't it RB2S?
I was just seeing if you were paying attention. No, I had a brain fart. Yes, absolutely, it's RB2S. That's why you should always check your work, and I didn't do that. It's 2 rubidiums and 1 sulfur. Thank you. I appreciate it when you point out the mistakes that I make. I am human. I make mistakes all the time. Do not be shy about saying, hey, are you sure about that? I screw up. So what if it's not one of the 1A, 2A, 3A zinc or silver ions? Well, then we've got the name of the cation and its charge in Roman numerals within parentheses, and then the name of the anion, just like we learned already. How do we know what the charge is? We have to figure it out from the charges on the nonmetal and the relative numbers of the atoms. And so this involves maybe a little bit of math. So let's do an example here. So CrBr3. We need to name this. So there's two ions. There's chromium and there's bromine, right? So chromium is the first one. So the element is chromium. Do your best to spell these things correctly. On the exam, it'll be multiple choice, so it shouldn't be too much of a problem. Then ask yourself, does chromium need a Roman numeral? It does, because it's not in groups 1A, 2A, 3A zinc or silver. So what I'm going to do here is I'm going to put the parentheses so I remember to come back and fill that in. I'm just going to leave a space. I don't want to deal with it just yet. And then I look at the second ion, bromine, so I change the ending of the name to bromide. So it's going to be chromium bromide, but I need a Roman numeral. So now I have to figure out what that is. You can't just look at the periodic table. So bromide, well, that's Br -1 from its position on the periodic table. And chromium, I don't know what it is. And the formula tells me I have 3 bromides. So there's 3 of those. So the total negative charge from the 3 bromide ions is -3, right? If there's a total of -3 charge, what must the total positive charge be? +3. I know from the formula that there's only 1 chromium ion in this formula. The total charge has to be +3, so that means this chromium must be +3. So it's a 3+. And that works. 3 -1 ions with 1 +3 ion, the charges will add up to 0. So the Roman numeral here then is 3. Any questions? Yeah.
May have missed this, but so the Roman numeral will always be the charge of the metal.
The Roman numeral is always the charge on the metal. A common misconception that students have is they think it's the number of atoms. And so they'll say, oh, well, there's only 1 chromium, it's chromium 1 bromide. But the Roman numeral is the charge on the ion. It's a chromium 3 ion, it's got a +3 charge. Figuring out this charge involves a little thinking, but it is not hard math, okay? There's not really any algebra or anything. If I gave you a problem like this in terms of little boys and cookies and sharing and stuff, you'd get the answer right away. So you can all do this. You just need to convince yourself that you can. If you want to hear the little boy cookie thing, I'll tell you later. So let's practice. Name this compound FeS. So the first element is a metal. It's an ionic compound. Of course, now we're only doing ionic compounds, but later they'll all be mixed up. So Fe is iron. Does iron need a Roman numeral? Yes. It's not in group 1A, 2A, 3A zinc or silver. I'm going to say that over and over and over again. So it needs a Roman numeral. Don't know what it is right now. I don't care. I'm just going to leave a space. Sulfur changes the ending of her name to sulfide. Now I go back and figure out what the Roman numeral is. I'm going to figure it out based on the charge on the sulfide ion and the relative numbers here. So I have 1 iron and I have 1 sulfur. I get that from the formula. The charge on the sulfur ion is -1. I'm sorry, -2. I wrote it correctly. 2-. Well, if one of each of these are going to cancel their charges, if their charges are going to add up to 0, what does the charge on the iron have to be? 2+. So this is a 2+ ion, so then the Roman numeral is 2. Iron 2 sulfide. Any questions? Yeah.
Do you always want the elements to be with a lowercase when you write them out?
That's a good question. Should these always have lowercase or should they be capitalized? So the names of compounds are not proper nouns. So the only time they would be capitalized is if you're starting a sentence iron 2 sulfide, then you'd capitalize the I. But otherwise, no. I'm not going to make a fuss about it, but that's how it is. And when you're writing it out, you don't really notice, but there's no space between iron and the parentheses. The 2 in parentheses is kind of part of this word, and the space comes after the parentheses before the second one. Any other questions? So here's a name. Let's write the formula. Ruthenium-4 oxide. Well, the symbol for ruthenium is Ru. And what does the 4 tell us? It's a 4 plus charge. It doesn't mean that there's 4 rutheniums. It means the charge is 4 plus. Then we have oxide, so that's O. And from the position on the periodic table, we know it has a 2 minus charge. So we see that these charges are not the same as each other. So we can do the crisscross thing. So if we do crisscross, what do we end up with? Ru2O4. Because this charge becomes the subscript here, that charge becomes the subscript here. What is wrong with this formula? It's not the lowest ratio, right? It's 2 to 4. Ionic formulas are always empirical formulas. And so we should simplify that. It's RuO2. That's the correct formula. If you're not crisscrossing and you're just thinking about it, so here I've got +4, and over here I need a total of -4. I can just kind of think about it and say, well, I need 2 of these to balance the charge on that. There's multiple ways of figuring these things out. You need to find one that works for you and just stick with it. Any questions?